In this video, we'll be talking about relations and functions. So you can see here we have some objectives for this lecture to determine whether a relation is a function, apply function notation, determine x and y intercepts of a function, determine domain and range, interpret a function graphically. So these are going to be foundational skills that we're going to develop and use for the rest of our course. Let's start with the definition of a relation. A set of ordered pairs, x and y, is called a relation in x and y. So we know that a set is a collection of objects, and the objects in the set are the elements of the set. So in this case, we're taking a set of ordered pairs. An ordered pair is just like this, where we write the parentheses. The first one is x. In this case, the second entry is y. We close the parenthesis. So the order matters, hence it's called an ordered pair. And the set of x values in this collection of ordered pairs, or this set of ordered pairs, which is called a relation, the set of x values is the domain, and the set of y values is the range. So we'll do an example here, and it will probably become a little bit more clear what I'm talking about. So table 1.1 shows the score y that a student earned on an algebra test based on the number of hours x spent studying 1 week prior to the test. First, the question asks us to write the set of ordered pairs that defines the relation. So we know that these ordered pairs, x comes first and then y. So I'm just going to begin. Each row in the table is going to represent one ordered pair. So I start with my curly bracket. My first ordered pair is 8, 92. And that ordered pair tells us that if a student spent 8 hours studying the week before the test, they earned a 92. Then, comma, the next element in the set is going to be 3, 58. So in this class, there was a student who spent 3 hours studying the week before the test, and they made 58. Then 11, 98 is another ordered pair. 5, 72 and 8, 86. So these are this is the set of ordered pairs. This is a relation because a relation is just any set of ordered pairs. Now we'll write the domain. The domain is the set of x values. So again, we'll start a set and we'll say, well, one of my x values is 8. I have 3, 11, 5, and then I have another 8, but in a set, I don't have to write the same element twice. If the element is already contained in the set, then I don't need to write it again. So the domain is just going to be 8, 3, 11, and 5. In fact, if I were to write the extra 8, this would still be the same set. 8, 3, 11, 5, and 8. I don't need to write that 8 twice. Okay. What about the range? So the range, again, the set of y values. So I'll start a set. I have 92, 58, 98, 72, and 86. So this will be my relation, my domain, and my range. Now, there's a special type of relation which we're going to be focusing a lot on in this class, and that special type of relation is called a function. So if we have a collection of ordered pairs, x and y, which as we know is a relation, we say that y is a function of x if for each value of x in the domain, there is exactly one value of y in the range. So each value of x in the domain, exactly one value of y in the range. And you can see it's often helpful when we have these very small discrete domains to think of a function in terms of this graphic where you have the bubble with the x values in it, the bubble with the y values in it, and you put these arrows. So if for each x here in the blue bubble, there's exactly one y in the yellow bubble to which it points, then we have a function. So right away we can see that this example here, where we have 3 pointing to 11 and 6 pointing to 13, negative 6 pointing to 9, is not a function. Not a function because there is an x value, negative 6, that has more than one y value associated with it. It's also helpful to think of functions in terms of tables sometimes. So you can see here the table where we have cities, and we're labeling that as x. Elevation of the airport, we're labeling as y. So we have Albany, and its airport has an elevation of 285. So we can think about this as an ordered pair. The first entry is Albany, the second is 285. We have another ordered pair, which is Denver, and the elevation of its airport, 5,883. Miami, elevation is 11. And San Francisco also has elevation 11. So we can write these as ordered pairs. And we notice that there are two cities that have the same elevation, the same y value. And that is perfectly fine. We didn't say in the definition that we couldn't have two x's sharing the same y value. We simply said that for each x, there can only be one y value, and there must be one, so it should be exactly 1. Okay? So we'll determine here if the relation defines y as a function of x. And we have two relations, two collections of ordered pairs. So in A, we have 3, 1, 2, 5, minus 4, 2, negative 1, 0, 3, negative 4. And for it to be a function, we need to make sure that each x has only one y. So if x is 3, then y is 1. If x is 2, then y is 5. If x is minus 4, then y is 2. If x is minus 1, then y is 0. Then I have if x is 3, then y is negative 4. And that seems like it should be a problem because I already said that if x was 3, then y was going to be 1. So this is not a function because 1 and negative 4 are not equal to each other. Now let's look at the next example, B. So if x is negative 1, then y is 4. If x is 2, then y is 3. If x is 3, then y is 4. If x is negative 4, then y is 5. That should be just fine because we have 4 different x values, and they are going to, in this case, 3 different y values, but that's perfectly fine. This is a function because for each x in the domain, there is exactly one y in the range. Okay, very good. Now let's talk a little bit about function notation. So the function notation that we're referring to is going to be this notation you've probably seen before, where we write f of x. And this notation indicates that we're giving our function a name. That name is f, and that this will be a function of the variable x. So f is the name, x is an input from the domain, then f of x, when we write this way, represents the corresponding output from the range, which is often the y value. And the one thing we want to be careful here is that we want to make sure that we don't get confused that when we write f parenthesis x parenthesis, we're multiplying. We are not multiplying. So this is just a special notation. It has its own meaning. It means a function of the variable x is called f. It does not mean that we're multiplying f with x. Okay, great. So let's see another example. Determine whether the relation is a function. Give the domain and range. So we know how to do that. So first of all, we have a collection of ordered pairs, so we have a relation. Let's start with the domain and the range. The domain is going to be the set 3, 6, 5. The range is the set 3, 5, and 8. And I apologize, the domain should be 3, 6, and 8. Coming from 3, 6, and 8 being the x values, then 3, 5, and 8 being the y values. Okay, and for each x in the domain, there were 3 ordered pairs. We have 3x in the domain. There is exactly one y value in the range, so this is a function. And we know its domain and its range. So that would be how we would determine domain, range, and whether or not it's a function if we have a set of ordered pairs, but we know from experience that we're not always going to have this collection of ordered pairs written out. A lot of times we're going to see something that looks like this. X squared plus y squared is equal to 169. So this is an algebraic expression, and we might be asked to determine whether this defines y as a function of x. So we know it will define y as a function of x if for each x in the domain there is exactly one y in the range. Let's see if we can figure out if that's true. So first I'm going to try to solve this equation for y. I have x squared plus y squared equals 169. I want to get y by itself, so I'm going to start by subtracting x squared from both sides. X squared plus y squared equals 169. Subtract x squared from both sides, so I have y squared is equal to 169 minus x squared. I have y squared, but I need y. So the opposite of squaring would be taking the square root. So let's take the square root on both sides. Square root, square root. And on the left side, we have the square root of y squared. And we should know that the even root of an even power gives us absolute value. So in previous classes in high school, we might have said that when we take the square root, we get plus or minus. But since we're in college now, we know that the correct way of saying that is the absolute value. So we don't write plus or minus, we write absolute value of y is equal to square root of 169 minus x squared. But the end result is the same because absolute value of y being equal to square root of 169 minus x squared means y is equal to square root of 169 minus x squared, or y is equal to minus square root of 169 minus x squared. So I see that for any particular x, I'm going to get two different choices for y. So for each x in the domain, there are two y in the range of this relation. So this is not a function. The relation is not a function. But it is still a relation, and it's actually a very important relation because this, in fact, is the equation for a circle with radius 13. So just because something is not a function doesn't make it a bad thing, but in this class we need to be able to determine when something is a function. If it's not a function, it may still be a relation. Okay. So one other skill that we want to pick up is finding x-intercepts, x and y-intercepts. And we're going to be using our function notation. We're going to be using the function notation quite a lot from here on out. So given a function, y equal to f of x, we want to be able to determine the x-intercepts. Those are going to be the real solutions to the equation f of x equals 0. So we set our function equal to 0 and we solve for x. And the y-intercept will be the value that we find when we plug 0 in for x. So graphically speaking, when we're talking about x-intercepts being where f of x equals 0, we know f of x represents the y value. Y being 0 means we're crossing the x-axis. So if you take a look at the picture of the parabola down here, you can see that graphically speaking, an x-intercept is where we cross the x-axis, and that makes sense because when we're crossing the x-axis, y should be 0. On the other hand, a y-intercept should be exactly where we're crossing the y-axis, and so it makes sense, visually speaking, that that should be when x is equal to 0. Okay, so if we have a picture, we can clearly identify the x and y intercepts. Now we want to be able to identify the x and y intercepts algebraically as well. So using this graph here on the right, we're asked to determine the function's domain, the function's range, the x-intercepts, if any, the y-intercept, if any, and the missing function values indicated by the question marks. So first of all, how do I know this is a function? Well, I can look at the picture, and the question that I'm asking myself is, for each x in the domain, and it looks like the domain here is all real numbers because this arrow indicates that it keeps going off to the left, keeps going off to the right, so any real number can be plugged in as an input. So the question is, for every x, is there exactly one y? And it looks like that should be true. So for this x I get a y, for this x I get a y, exactly 1. So this is a function, and we want to determine the domain. Well, as I just said, these arrows indicate that it's going off to the left, off to the right forever. So the domain is all real numbers. And how do we write all real numbers? Well, we can write the interval negative infinity to infinity, or we can write this script r. Then we want to determine the range. So the range is the collection of all of the y values. And I can see from the picture that the graph appears to start at -1 And it attains all of the positive y values and all of the y values larger than 1, but it doesn't get any smaller. So from the picture, it looks like it starts at exactly -1 and goes to infinity. Then the x-intercepts, we talked about this is where the function crosses the x-axis. So the x-intercepts occur when x is equal to 1 and y is equal and x is equal to -1. But we want to remember that when we're talking about x-intercepts, we're talking about ordered pairs. So we want to write them as ordered pairs. So we have x equals -1 and y is 0. We have x is +1 and y is 0. Then the y-intercept. Again, I want to write ordered pairs. I know that my x value is going to be 0, so I can start with that. And then where does the graph cross the y-axis? Well, it crosses it at exactly y is -1. Okay, finally, we want to fill in the missing function values indicated. So it's asking us to find the function value when x is -2 and the function value when x is 2. So this notation, f parenthesis -2 parenthesis, means what y value do I get when x is equal to -2? So let's go over to x is equal to -2 and kind of draw this dotted line and see where does that cross our graph. Looks like it crosses it here. So when x is equal to -2, y is equal to 3. We just count up, so we say that's equal to 3. What about when f is equal to 2? I'm going to do the same thing. I'm going to go over 2 units to the right and see where does this line cross my graph. And again, it looks like it is at y is equal to 3. So I have answered the question. Now, again, if we have a collection of ordered pairs or we have the picture of the graph, we can usually find the domain and the range. What about if we're just given the rule of the function or the expression of the function? So we'll have some guidelines here to find domain of a function, and they are to exclude any values of x that make the denominator of a fraction 0. The denominator we talked about already is the bottom of the fraction. We can't divide by 0, so any x that would cause us to divide by 0, we take it out. We also want to exclude values of x that make the radicand negative with an even indexed root. So if we're taking square root, fourth root, sixth root, etc., then we have to make sure that we know that we don't know how to take the square root of a negative. So whatever's under that square root or fourth root or sixth root cannot be negative. Okay, so we have a couple of functions to practice with here. Function a, f of x is equal to x minus 2 over 3x plus 1. So the 2 tips I had for finding the domain were to look out for fractions, make sure the bottom's not 0, and look out for even indexed roots like square roots, fourth roots, sixth roots, and so on. Make sure that the inside is not negative. So when would the bottom of this fraction equal 0? That would be if 3x plus 1 equals 0. So if 3x plus 1 equals 0, then that's going to be a bad point. So I can solve this equation for x, and I know that the solution to this equation will give me the bad point. So I will subtract 1 from both sides. I have 3x equals -1, and x is equal to -1/3. So x equals -1/3 is the point that I want to exclude, And I don't have any other problems because I don't have an even indexed root. So I'm going to say that my domain is all real numbers except x equals minus 1/3. How do I write that? Well, I want to think about the number line. And somewhere here is minus 1/3. And I know that I need to remove that point, so I'm going to have an open dot. But everything else is fine. Everything to the right and everything to the left is fine. So if I wanted to express this in interval notation, I would say, well, I can take everything from negative infinity all the way up to minus 1/3. But then I have to stop. I use a parenthesis here. But I also want to take everything starting at negative 1/3 and going up to positive infinity. That's all fine. So the way that we're going to denote both of these is with this symbol that looks like a U for the union. So this U symbol, which stands for union, it indicates that it is both of these sets. We're combining these two sets. So that's all real numbers except for minus 1/3. All right, let's look at part B. B is g of x equals x squared over 5. So I need to make sure that the bottom of the fraction is never 0. So any point that would cause the bottom to be 0, I would want to exclude, but the number 5 is never equal to 0, so I don't have to exclude anything. I also want to look out for even indexed roots, but I don't have that. So the domain here is just going to be all real numbers. I have no issues, so I can write the interval negative infinity to infinity, or I can write r. Okay, C, k of x is equal to the square root of x plus 3. Okay, well, square roots, or fourth roots, or sixth roots, even roots, are one of the things I'm looking out for. So the tip above told me that when I have this situation, I need to make sure that what is inside the root, so this x plus 3, must be not negative, because I don't know how to take the square root of a negative. So I will say I need x plus 3 greater than or equal to 0. It's fine if it's equal to 0 because the square root of 0 is 0. So if x plus 3 is equal to 0, that's fine. If it's greater than 0, that's also fine because I can take square roots of positive numbers. I just need to make sure that it's not less than 0. So now I have an inequality, and we know how to solve inequalities. I'm going to subtract 3 from both sides and say x is greater than or equal to negative 3. And then I want to write that in terms of interval notation. So I can draw the number line. So I'm picturing the number line, and somewhere here is minus 3. I said I'm allowed to be greater than or equal to minus 3, so I know that that's closed dot above minus 3, and greater than, so I go to the right. Okay, so this red arrow is showing me the domain, and I just need to express that in interval notation. So I know I'm starting at minus 3, and I'm going all the way up to infinity. And then I just have to decide whether I'm using square brackets or parentheses. Since I have a closed dot, negative 3 is included. I'll do square bracket, and infinity always gets parentheses. Okay, not bad. Finally, we have part D of the question. P of x is equal to 2x squared plus 3x. So the things I'm looking for, again, would be dividing by 0. I don't see any fractions here, so that shouldn't be a problem. And taking even indexed roots, I don't see any roots here. So this should also not have any bad points. So I can take the domain to be all real numbers. I can plug in any real number that I want. So that's the interval from -infinity to infinity, or R. So we've talked about how to determine if a relation is a function if we have the collection of ordered pairs. But sometimes we may have just the graph. We touched on this a little bit before. If we have the graph, if we have the picture of the relation, and we want to determine whether or not the relation defines a function, we have what's called the vertical line test. So the graph defines y as a function of x if no vertical line intersects the graph in more than one point. So let's take a look at this first picture here on the left. I want to be able to draw vertical lines, as many as I want, anywhere that I want, and make sure that no vertical line is crossing more than once. And you can see from this picture that it is passing this test. So according to this blurb here, that means this is a function. So let's talk about how this connects to the idea that we already know about functions. So before we said if we wanted to determine if something was a function, we needed to make sure that for each x, there was exactly one y. So each vertical line that I've drawn here represents one x value. And when I'm checking that the vertical line doesn't cross the graph more than once, what I'm checking is that for each x value, there is exactly one y value. So for each x value in the domain, exactly one y value in the range. So this vertical line test is an equivalent notion to the idea that we already know about how to determine if something's a function if we have the picture instead of, say, the collection of ordered pairs. Okay, let's look at the second one. So I need to be able to draw vertical lines, as many as I want, and check that none of them intersect the graph more than once. Well, right away I can see here that I've already got an issue because this vertical line is intersecting the graph in 3 places. So let's say that this line is the y-axis. I didn't draw it exactly straight, but let's say that this is supposed to be the line x equals 0, which gives us the y-axis. Then when x equals 0, for this relation, I have y equals -3, I have y equals 1, and I have y equals 3. So this is clearly not a function. Because it fails the vertical line test, and therefore there are x values in the domain so that they have more than one y value in the range. Okay, and finally, this third picture here, I'm going to do the same test, draw as many vertical lines as I want to, and check, is each one crossing the graph exactly once? And it is. So this is also a function, because for each x in the domain, I have exactly one y in the range, and that is what I need to be a function. So what about if I have an algebraic expression like x plus 3 everything squared plus y plus 4 everything squared equal to 1? Well, we've done an example sort of similar to this when we had x squared plus y squared equals 169. We want to try to solve this for y and see if we get exactly one y value in the range for each x in the domain. So I'm going to start by subtracting this whole term, x plus 3 squared. don't have to expand anything. Just subtract this entire term from both sides. And that's going to give me, on the left side, y plus 4 squared. And on the right side, 1 minus x plus 3 squared. Let me try to get my pen here. Okay, so on the left, y plus 4 squared. On the right, 1 minus x plus 3 squared. And then I know that because I'm trying to eventually isolate y, I need to get rid of this square. So I need to take the square root on both sides. So I'll try to take the square root on both sides. And again, by now I know that because I'm taking an even indexed root of a even powered term, that's going to give me absolute value of y plus 4. Should be absolute value. And that's equal to, on this side, square root of 1 minus x plus 3 squared. I don't have to simplify that. I can leave it. So this tells me that I have y plus 4 equal to square root of 1 minus x plus 3 squared, or, because I had absolute value, maybe it's that y plus 4 is equal to minus square root of 1 minus x plus 3 squared. So then, if I subtract 4 from both sides, minus 4, minus 4, do the same thing for this one, minus 4, minus 4. Then finally I get to say that y is equal to square root of 1 minus x plus 3 whole squared minus 4, or y is equal to square root of, it should be minus square root of 1 minus x plus 3, everything squared, minus 4. And that's two different values for y for any one x that I plug in. So this is not a function. It does define a relation because we could write down the set of ordered pairs, but it is not a special type of relation called a function. Okay, so let's connect these concepts a little bit more. We want to fill in the blanks. A set of ordered pairs x and y is called a blank in x and y. This was our first definition, so we know that a set of ordered pairs in x and y is called a relation in x and y. The set of x in the relation is called the domain. The set of y values in the relation is called the range. So we're used to perhaps talking about domain and range of functions. Functions are just special types of relations. So what we're getting here is that this idea of domain and range is actually defined more generally for any collection of ordered pairs. It just means the set of x values is the domain, the set of y values is the range. And we know that if this relation is a special type of relation called a function, then for each x in the domain, we'll have exactly one y in the range. Okay. Question 2. Given a function defined by y equal to f of x, the statement f of 2 is equal to 4 is equivalent to what ordered pair? So this is making sure that we understand our function notation. The way that we read this, f of 2, it basically means if 2 is the x value and I'm inputting 2 into the function f, then the output y is going to be 4. So the ordered pair is x is 2, y is 4. All right. So we want to check that we know how to determine whether a relation is a function. And in this example, we're given a table. So let's try to write down these as ordered pairs. So let's write down the relation in terms of its ordered pairs. So I'm going to start a set, and I'm going to say my first X value is Tom Hanks, and he corresponds to the Y value 5. 5 Oscar nominations for Tom Hanks. My next X value is Jack Nicholson, and he corresponds to the Y value 12. Then the next X value is Sean Penn, and he corresponds to the Y value 5. And finally, my last X value is Dustin Hoffman, and he corresponds to the Y value 7. So for each X, my X are Tom Hanks, Jack Nicholson, Sean Penn, and Dustin Hoffman. Do I have exactly one Y? I do. So this is a function. And we want to make sure that we don't get confused by the fact that Sean Penn and Tom Hanks have the same number of Oscar nominations. That's okay. It's still a function because each of them, we can say exactly how many Oscar nominations that they have. There's no question. Does Sean Penn have 5 or 6 or 7 or 10? We know it's exactly 5. So this is a function. Okay, we want to determine if each of these is a function. So because we have the graphic, our best bet is probably going to be the vertical line test, which is our graphical way of determining if each X in the domain corresponds to exactly one Y in the range. So this first picture, it looks like, I'm just going to say yes, it's a function. Now what about the second picture? The second picture might not be exactly what we're used to thinking about a function. It's just a bunch of dots. But it still satisfies this property because for each X in the domain, there's exactly one Y in the range. So yes, it's a function. We've already seen that a picture of this type is not a function because we've got at least one X in the domain, like X equals 0. X equals 0 has 3 different Y values in the range. So it's a relation, but it's not a function. How about this straight line? Well, I can still do my vertical line test, and I can see that yes, this is a function. So a horizontal line is a function. A vertical line is not a function because it fails the vertical line test very badly. So it's not a function. It is a relation, and this is actually an important type of relation to know because any vertical line can be expressed as X equals, so in this case 2. So X equals 2 is a nice equation. It gives us a nice graph, but it's not a function. All right, what about this function? Well, I think I have a problem here. If I draw this vertical line, I can see that I've got 2 closed dots here and here. Again, when I draw the vertical line X is equal to 1, I have 2 closed dots, and so on. So this is failing the vertical line test because, for example, X equals 1 in the domain, it corresponds to 2 different Y values in the range. It corresponds to -1 and +1, so that's not a function. But I can fix that issue by making these open circles. Now I can see that when I do the vertical line test, for each vertical line, no matter where I draw it, it passes through only 1 because this open dot is not a Y value. So this is a function. What about this type of representation, where we have the bubbles? So In this first picture, the domain is -8, and the range is 3, 4, 5, and 6. And the ordered pair -8, 3 is in the relation, -8, 4 is in the relation, -8, 5 is in the relation. So this is clearly not a function. Because in order to be a function, -8 could correspond to only one value in the range. What about if the roles are kind of reversed? We have 5, 6, 7, and 8, so 4 values in the domain, and they all point to the same value in the range. Well, that's perfectly fine. This is a function because for each x, say x is 5, I have exactly 1 y. If x is 6, I have exactly 1 y. So this is fine. So this is going to be a very important example, and if you ever find yourself kind of forgetting how to determine if something is a function, I think this is a type of example that you could quickly think about to kind of remind yourself. The bubbles on the left, not a function. The bubbles on the right are a function. Okay, if we have an algebraic expression, we should be able to check. So I have something like y equals x plus 3. For each x, am I going to get a different y? Absolutely. So just to convince myself, I can try plugging in a few examples. That's not really sufficient, but it will help us see that no matter which x I put in, say I put in 0, then I get out 3. If I put in 1, then I get out 4. If I put in 2, then I get out 5. So there's only one y that's going to come out for each x. So let's think about b, y is equal to absolute value of x. So if I put in an x and it's positive, say x is equal to 3, then I know that the absolute value gives me y equals 3. If I put in x equals -3, then absolute value gives me still y equals +3. But remember, we said it's perfectly fine if two different x values have the same output, the same y value. And there is no question, for any x that I put in, we know that it's going to give us exactly 1 y. So this is a function. We can also think about the graph of y equal to absolute value of x. And it looks like this. So where we have 1, 1, 2, 2, -1, -1, -2, 2, for example. This is x, this is y. And then we can see that it would absolutely pass the vertical line test. How about if x is equal to absolute value of y? Well, then we would have, for each x, two different choices of y. So we'd have y is equal to x or y is equal to -x for each different x that we put in. So this is not a function. And if we thought about its graph, then it would look like this, where we'd have 1, 1 and 2, 2, but we'd also have 1, -1 and 2, -2, and this would clearly fail the vertical line test. Okay. So this will be another important example for you to think about and remember. We have y equals absolute value of x. This passes the vertical line test, but if we have x is equal to absolute value of y, it fails. Now let's practice our function notation just a little bit more. We're given a function called f, a function called g, a function called h, and a function called k. And we want to be able to evaluate these values. So for a, it asks us for k of -2. K of -2 means putting x equals -2 into the function k. So that's going to be square root of -2 plus 1. And I can simplify under the square root. So it's square root of -1. And we don't know how to take the square root of a negative, at least not yet. We might learn a little later in this class. So we're going to say this is undefined. What if I put in k of -1? K of -1, again, I just replace the x by -1, so this is square root of -1 plus 1, which is square root of 0, and square root of 0 is 0. So k of -1 is equal to 0. If I put in k of 0, I get square root of 0 plus 1, that's square root of 1, and that's 1. If I put k of 1, I have square root of 1 plus 1, that's square root of 2, and we just leave it as square root of 2. If I put in k of 3, I have square root of 3 plus 1, which is square root of 4, which is 2. So I have 0, 1, square root of 2, 2, and just the first one was undefined. So what about if we're given the function as a set of ordered pairs? So we have the ordered pair 2, 3, 9, 7, 3, 4, -1, 6, and we want to determine f of 9. Well, the idea is the same. F of 9, this notation means which y value do I get when I plug in x equals 9? And it's 7 because I find the ordered pair where x is 9 and I just read the y value. If f is equal to -1, again, I just find the ordered pair with -1, the x value, and read the y value, that is 6. Now another thing we want to get comfortable with are word problems. So here's one. At a restaurant, if a party has 8 or more people, the gratuity is automatically added to the bill. If x is the cost of the meal, then the total bill, C of x, with an 18% gratuity and a 6% sales tax is given by C of x equals x plus 0.06 times x plus 0.018 times x. Then evaluate C of 225 and interpret the meaning in the context of this problem. Okay, sounds good. So this is an example of using function notation. We're naming our function C of x. So evaluating C of 225 just means replacing x by 225 in the function. So I have 225 plus 0.06 times 225 plus 0.18 times 225. And I can simplify that a little bit. So that's 225 plus 0.06 times 225 is 13.5 0.18 times 225 is 40.5. So this is 225 plus 40, 54. And that is equal to 279. So C of 225 is 279. That's the first part of the question. The second part of the question asks us to interpret the meaning of this in the context of the problem. So they told us that C of x was a function of the cost of the meal. So the total bill, you not only pay for your meal, but you pay your tip and you pay taxes. So this tells us that if a meal for a party of 8 or more costs $225, then the total bill will be $279 after taxes and tip. So when we're answering a word problem, and especially if it asks us to interpret the meaning, then we absolutely want to answer in a full sentence and give as much detail as possible, because this is giving us a chance to express our mathematical ideas and show our understanding. Okay, what about a student decides to finance a used car over a 5-year period. After making a down payment of $2,000, the remaining cost of the car, including tax and interest, is $14,820. The amount owed, y equals a of t in dollars, is given by a of t is equal to 14,820 minus 247 times t. So we have a function called a. It is a function of the variable t, and t is the number of months after the purchase. Then determine the t-intercept and the y-intercept and interpret their meanings in context. So a of t is equal to 14,820 minus 247t. That's the first thing that we need to get out of this question. And then we need to find the x and y intercepts, or the t and y intercept. So I know that if I plug in t equals 0, and this t is acting like x has acted in some previous examples that we've done, that should give us our y-intercept. So that would be 14,820 minus 247 times 0, which is 14,820. That tells us that the ordered pair 0, 14,820 is the y-intercept. Now if I want to find the t-intercept, I'm going to set the function equal to 0 and try to solve for t. So 14,820 minus 247t. So add 247t to both sides. I get 247t is 14,820. So t is equal to 14,820 divided by 247. And that turns out to be 60. So that tells us that 60, 0 is the t-intercept. Okay, good so far. Now, the question has asked us to interpret these intercepts in the context of the problem. So again, we're going to try to write a full sentence explaining what does this mean. So we're told that this function a of t gives you the amount of money you owe on your car loan after t months. So t being 0 means that we just took out the loan. The y-intercept, so if we just took out the loan and we owe $14,820, that should tell us that the total amount of the loan was $14,820. So we bought a car for $14,820. Then after 60 months, the amount owed is 0. That's how we interpret the t-intercept. So the t-intercept tells us that after 60 months, which is 5 years, we'll pay off the loan. All right. And that should be the last example. So we've learned a lot of skills in this lecture note. We're going to stop here and we'll pick it up in the next lecture.